Welcome back, everyone. The next on stage is Kevin, who's a colleague of mine, talking about LLMs and incidents.
Indeed. So, good afternoon, everyone. Hope you enjoyed the break. So I'm going to talk about, well, this is the title, right? Leveraging CodeQL at scale and LLMs at scale. That's the key part of it. And the reason why I'm going to talk about it can be summarized in this little picture. So take a look. And what you see is easy, right? Just squares in colors. If I now ask you, look for a specific pattern of these pluses, it suddenly becomes a bit harder. So for example, 3 pluses in this ordering, can you spot those in any type of color? That's surprisingly hard. But if I do this, then suddenly it's quite clear. Then they stand out. You can swap them, you can rotate them. You know, there are differences of sort of organizing them, but the ordering of those 3 pluses together, they can be seen now. And this is what I'm going to talk about, but then in code. So my name is Kevin. I'm a software engineer at ING and then the Netherlands, also working at the global side of the bank. And yeah, I really like software languages, and software analysis, and parsers, hence the tree-sitter joke. We use this technology to look at our software and then come up with a reliability angle to this. And what that actually means, I'm going to tell you. But first, a bit of ING. So we're hosting this, but I don't think anyone ever really showed this yet. So we're big. So we have lots of people working in tech. We have lots of code, many microservices, and an enormous load of pipeline runs a week, large numbers. So you can imagine if you ask yourself something about where can I find anything in code? If you look at these numbers, there is a lot of code, right? You can probably imagine. So this question becomes surprisingly hard. And my story starts with an incident, because it's SRE, right? We like incidents, and especially solving them. And at some point we had an incident, and that was a bit sad. So we at some point made a mistake, and it got a lot of attention, you know, the unwanted kind of attention. And we figured, so what can we do to solve it? We did our post-mortem, as we always do, and we took it from there. And if you dump it down, you cut away everything. One of the contributing factors was a coding error. Specifically this, simplified of course, but it had to do with Java, Spring, dependency injection, mutable state. Probably something you will recognize if you've ever done something in this area. And yeah, that happens. And the solution to this problem is equally simple. You just ensure that this state you're mutating is not an instance variable, but a local variable, and you're done. It's that simple. But that's the real key thing. If you have all that lines of code, how can you ensure that you do this in a way and at scale that it really is being addressed properly? So we were looking into this and we figured, hey, this is something about a software pattern. And patterns we can look for, right? There is tooling for that. For example, CodeQL. There's also RESTful. There is OpenGrep. There is many of these kind of things that have a shape and form of looking into patterns. For reasons that I'll go into later, we had a preference for CodeQL. So we went to work and we started to model the problem that we encountered in a general way. Can we express the key characteristics of this problem in such a way that we can look at all of the other code that we have, or at least a section of the code that we have, to try to find the same problem. So we went to work, we wrote a query, we iterated, and then at some point we were sort of happy because we could consistently find the problem in the known culprit, the code base that had the problem, and in a way that we were sort of okay and satisfied with how general and at the same time specific it was. General in the sense of it should match any other similar type of problem, specific in the sense of try to limit the amount of false positives you get. So we went to work. So we looked at our code, and we have a lot of repositories. So then the question was, okay, so how can we sort of scope this? Because we're evaluating this product and we don't have the full scope. So let's make a smart selection and cut down the scope of our experiment to a smaller scale. And eventually we settled upon a bunch of Java APIs, about 850 of them. And in there we found 162 other instances. And those instances, they were variations of the same problem. All different, in different code bases, but they stood out. So we looked into them, and we analyzed them, and we figured out, these are indeed things we should fix, and they're latent, right? They're aware, they exist in our code base, but not necessarily causing problems. For example, because it's a low load type of component. So that was quite fun. It gave us some very good results. So we figured out, okay, what can we do next? So first of all, we started to look into the context as to how we approach this. And CodeQL, I already mentioned, we selected that tool for reasons. Well, these are some of the reasons. So we want something that is scalable. So 1,000 repos is nice, but it's not the scale of ING. We want to be able to address the full scope. And SAML is something that, at least CodeQL is something that we think can address that. It's also a product now acquired by Microsoft, which means a very nice integration in the Microsoft and GitHub ecosystem, as some of you probably will know. And there is a large community, so a large open source community that is very actively working on this in the open, so we can really see what's going on and also be involved there. And finally, the product itself, although closed source, is relatively open. So in terms of priority setting, in terms of discussions, in terms of where can we see the product moving, there is lots of discussions with people interested in this, and you can sort of influence what's going on. So all of that really stood out to us, and we really liked it. And to give you an idea of what it means to be active and open, so this is a screenshot at some point of their Git repo. Lots of commits, very active. This is pretty much what you see if you go there. Can recommend. And in terms of research, that's also very nice. Lots and lots of people in the academic circle start to use the tool in various different settings to try to put it to work. For example, in security research, but also in other types of reliability-related perspectives, let's say. And of course, you see a large uptake, and that has to do with the Microsoft acquisition and how it positions the tool in the ecosystem, specifically by making it free for open source projects. So why did we look at it? So first of all, we don't want to make the same mistake again. If you look at this problem, okay, that can happen, right? But the key thing is, how can we learn from this and prevent it from happening again? We don't want to make that mistake again, and preferably not like 20 times in a period of a couple of years. Of course, we learn from things. Of course, you try to improve. But at some point, there is someone in the company who hasn't experienced this or learned about it, and they will make the same mistake, right? And you can't blame them for that, because that's just what happens. You can rely on tests, sure, but tests don't always catch all the little details. You have, in this specific example, there's also characteristics like enough load to sort of replicate the problem. Then there's consistency, right? Even if you replicate it, does it always happen? Or is it just a flaky test that needs to receive all their attention? Regardless, it's something you can focus on, and this is a way to do that. The other thing is that we can use it to guide us in driving refactorings or tasks you need to do by looking at how often things occur. So for example, if you're building some sort of component, you're using some sort of a specific dependency, or you're using a certain pattern and you want to get rid of that for reasons, this is a way to sort of figure out A, where it is, and B, how often it occurs. And if you realize this is something that occurs often and it's undesirable, and I know where it is, it could be a driver to say, for example, write an open rewrite recipe to do this migration away from the pattern you don't want to a target state that you do want, and then apply these migrations to the repos that have this problem. Identifying contributing factors. So there are also lots of incidents where there is something that's in itself smelly, but not necessarily causing the problem, but you still want to improve upon that. Again, a very nice way, a very nice thing to model as a pattern, search for, and then apply, find it and take care of it. Finding the needle in the haystack, essentially. And finally, surprising nice thing about this is propagation of learnings. So say that you have a repo, and this incident happened, you don't necessarily know about it, but you do receive a notification. Hey, we saw this in your repo, there was this incident, this pattern contributed to that, maybe you want to make an improvement here. That's actually a very nice type of feedback to get as an engineer. But how does that relate to finding a bug? And I know these are insects, right? Bees, but it was the best picture I had. There it got interesting. So Azure DevOps, you have one repository, you have a build pipeline. That's sort of the scope of CodeQL if you use it there. Also advanced security as they called it back then. Code security now. It's a one-to-one mapping. So it works, you can do it, but it doesn't really scale across many repos. So on GitHub, there is a variety that does scale. They call it multi-repository variant analysis, or MRVA. That has an upper limit of 1,000 repos. It works in our little example, but not the full scale of ING. So we need something else. ING has many repos, many thousands of repos. So how do you cater for that? And also, because of reasons, we did not want impact on individual pipeline runs. So if you, as a team, would have a sort of slowdown because, we decided to scan all your code for things, the average team will not be happy, right? You suddenly increase the pipeline run by X time, or make it asynchronous but still have it in their scope. We'd rather not have that, so we figured we need something else. So eventually we settled upon essentially a small system that runs outside of the CI/CD flow, and it can be used to essentially clone a repo, build this CodeQL database, and store it, and also given a query or a set of queries, evaluate it against the database, and then produce results. It's very simple. I won't go into the details of that because that's not the interesting part of this talk. The more interesting bit is, if you have these findings and you scale that up over these thousands of repos, how do you cater for that? Because suddenly you have thousands and thousands of results that need to be processed by humans. That's not so very nice. So that's where the LLM of the title comes in. We of course, jumped in on that bandwagon and explore the benefits and the potential value there. And there we did put the human in the seat. So at the end of the day, we don't want to blindly apply changes here throughout, ING. We want humans to make these assessments and propagate them from there. And to give you an idea, so this is some example data. We run a scan across a large set of repos. You get thousands of results. We use a bunch of heuristics to get rid of a whole bunch of noise. For example, anything in a test class is not relevant. And you can make up your own heuristics. But eventually down the line you get much less noise. But still so much that you want some tools to help you. And for that we built this code analysis workbench, working title. And it's essentially a front end to help you sort of go through these findings. This is what it looks like. It's a very simple web application, no fluff. It only shows you, okay, there are these repos, there are these results, they happen at certain files in certain versions. Have a look. And on the right, there's a so-called expert verdict and a model prediction. And the expert verdict is the human part, and the model prediction is, of course, the model side of things. So what does that look like? So if you take any kind of finding that you could have, you see something like this. So this is one of the simplest examples you can get, boxed integers in Java, and comparing them. Right? We all know that you should do this with dot equals, and many people do equals equals, and that works because of caching, essentially. You can debate about how impactful this is. That's not the point of this. But you do have it, and you need to do something about it. So what we did is we defined a bunch of system prompts according to our risk profile, where we say, hey, these are things we think are important. Please assess these findings in the context of this risk profile and come up with a verdict. And these assessments, they are basically provided with a context that consists of the CodeQL result, in the sense of the code snippet, file path, potentially a trace until of the CodeQL result itself, but also the high-level description, as well as the QL context of the finding. And all of that together gives you a reasonable way to sort of come up with such an assessment. I'll get to in a bit more detail. So, taking all that context, we put it into a bunch of different conversations, in this case 3. And those 3, we essentially made different personas or archetypes or whatever you want to call them. So individual assessments of the same thing, but with a different focus or like attention points. So you get different perspectives of the same finding, and essentially you get an ensemble that together come up with sort of their irrespective views, and that you push together again and say, hey, I have these different perspectives of the same finding, and I have the facts, like the actual code that happened. Can you try to come up with a patch that takes all of this into account? And that also takes severity into account, for example, based on what the model initially assessed. Potentially, depending on how the flow we do, we can also include the expert verdict of the human in it or not, but that's a choice. And how that looks is essentially like this, right? This is what you expect. There is a fix for this problem. You can solve it. The interesting thing is, though, that sometimes this is very nuanced. So with the equals equals thing, that's not really interesting. This is slightly more interesting. So when looking at this, for example, you could ask yourself, like, where does this value come from? Or is there some other context that I need to consider while assessing this? So in that, if you want to go into that detail, you can essentially chat with your code. As we all are sort of aware of, that is quite nice to do. And you can use it to come up with different perspectives of this thing you're looking at to figure out, hey, is this something that I consider a true positive or a false positive? And you can take it from there. And finally, you need to feed this back to engineers. You can create a PR. That's sadly something we haven't automated yet, in the sense that I can only show a demo. But that has to do with policies rather than technology. So let's just say we're working on that. And what this looks like is this. And for some of you might know this. So this is a copy of a codebase on GitHub, and it's called DigiD broncode. So we applied the same pattern there, and there was apparently some sort of internal endpoint dealing with CSVs, so nothing, for us consumers, but it did exhibit the same pattern. So we applied our query there. We got a patch. This was the patch. We applied it. Pull request was created. And then you have something nice to communicate. A tangible improvement and an explanation as to why this is a problem. So, what does this mean? What can we do next? So, like I said, right, so the PRs, we don't really deliver them yet, honestly. So, that's a bit sad, but we're working on that. Besides that, there is also, in the meantime, a lot of product development on the tooling provider side. So, for example, GitHub Code Security and Code Quality are now products. On Azure DevOps, there is also some integration with the same products. you see different sort of ways of dealing with the same problem, which is essentially getting this code analysis feedback and pushing it back into your developer flow, for example, in a pull request, and sometimes even locally. So those are things we are exploring. There's ING specifics. As you can imagine, we have certain guidelines or best practices within the company. So we're now exploring if we can encode these kind of things into these custom patterns and then apply them across the repos. And also quality guidelines. Just give people guardrails or best practices or advice on how to do certain things that can help to sort of improve over time your code base. Another thing is extending CodeQL. So due to the quite open nature of the tool, it gives you, let's say, extension points to really build your own stuff. Queries is obvious, right? I mentioned that a couple of times, but they also allow you to extend so-called extractors. And that is very interesting because that essentially gives you the tools to implement your own programming language as the most extreme end of the spectrum. So say you want to support, I don't know, COBOL, which is not supported, and say that ING wants it, then you could invest in that if you want. But more lower hanging fruit would be specific stuff. Like, for example, I want to look at these specific set of YAML files or markdown files that contain stuff related to ING that are very specific and not necessarily parsed. Let's stick with markdown because YAML is a bad example. But if you do that, then you can use it to sort of extend this behavior and allow you to check for other things, not necessarily programming language. So anything in your Git repo can be in scope. And that's extremely exciting because you can use it to really check for things automatically and at the level of skill that is hard otherwise. So that's what I wanted to talk about today. If you have any questions, then feel free to ask them. And otherwise, thanks for your attention.
Hi, thanks.
Hi.
I would like to ask about the static code analyzers, SAS, SonarQube, weather security, or so. What's your take? You choose this path. I'm pretty sure there is the value.
Yeah. So there are many tools indeed, right? And they all explore the same space, and all of them have their strengths and weaknesses. So that's pretty clear. And at the end of the day, all of them are great, to be honest, right? I just use one would already be better than to use none at all. There are a few differences though. So for example, CodeQL made a split between the analysis phase and the so where you apply queries and let's say the build phase where you take the source code and build a model. And that's actually a step that usually takes a long time. Most of the tools like SonarQube sort of integrate that into a single step. So if you want to run a query, you always need to scan all the code and then build that model internally and then apply the rules you built. If you can split that and just download all these databases quickly and then apply these queries, you have an extremely fast turnaround time to scan for queries. So that's one. And the other is the expressivity of the CodeQL query language. It's a domain-specific language, a logic programming language with object orientation in it. It's a bit weird, but it's extremely nice to express these code patterns in it. Much nicer, at least, than writing essentially a bunch of visitors for the Java AST for SonarQube, for example.
Yeah, hi, Sudesh here from VicaWorks. I have a question because you said you have 1,800 repositories.
In that sample scope, yeah.
And as I understand it correctly, you are downloading all the repositories and putting all the abstract of that data into a single database. How do you manage that security-wise, or what's the point of view from the security officers on that?
Yeah, that's a good question. So we're actually in a specific closed-down environment that has 0 access. So that's one. So and it can only access the code. That's the only interaction you can have with it. So that's 2. And then in terms of like what you can do with it, the owner of the data is the same owner that already has the source code, and as how we model the organization. So it doesn't leave semantically the organization that owns that data. But indeed, otherwise those things would be problematic.
Thank you for the talk. Which LLM did you go with? Like, was it? Did you do any analysis, like comparison?
Yeah.
Is there an overhead of like maintaining it and even like swapping it out with like something new and better?
Yeah. So we try to rely on as little as possible. So only chat API, let's say, and a bit of tooling support to format the patches, essentially. And as to what models we used, we only used GPT-4 and 4.1, and that had to do with that we could use those models. But that's also a regulatory sort of thing. Nowadays we can use more, but we haven't explored that yet. That's relatively recent. But even those models were already quite good, better than we expected. So that was the good news.
Yep. Thank you for the talk. I was wondering, do you have any insights on how much it costs to add this? And is this cost scaling linearly for the amount of repositories or in a different way?
Yeah, so there are two factors to this cost, right? So there's the product license of CodeQL. That's the most expensive part. And indeed, that is linear to the amount of people you have, essentially. That's their pricing model. And then there's the cost of the, let's say, the infra bit to run the analysis. That diminishes compared to license costs. So, yeah, that is increasing if you increase the scope, but license cost is the one that defines it.
Final question. Anyone?
So the results are kind of a one-time exercise that you did.
Yeah, so in what I showed you now, indeed, we have, but that's a completely separate story, but we sort of envision this to be fed back into, well, the engineering workflow, let's say. So indeed, no matter what you do, these findings should end up in your pull requests regardless.
So that was the answer for my second question. How do you ensure that the code the code with problems will not reach even the repo before?
Continuous monitoring.
Yes, exactly.
Yeah.
Thank you.
Yes, thank you, Kevin. And